Friends, today we will study the tangent stability analysis of a multi-machine system using a classical approach. We shall address to some of the important issues related to the tangent stability analysis of a multi-machine system. I shall discuss the node elimination by matrix algebra, classical model of the system. Using that model, we will develop the power output equations of generators in the multi-machine system. Then we will write down the swing equations in the multi-machine system, and then for tangent stability analysis, whatsoever preliminary computations are required to be made, that we will discuss those. One of the requirement while pursuing the multi-machine stability problem is the elimination of some nodes in the system where there is no current injection. That is, if you have a system, right, and at some nodes in the system, if there is no injection, then these nodes can be eliminated. Okay. Now, to understand how these nodes can be eliminated, we start with the general system, and the mathematical model of the system is expressed as I is equal to y bus into V, where I is the current vector and V is the voltage vector. That is, I are the currents which are injected at the buses and V are the bus voltages. Okay. Y bus is a matrix which is a square matrix, okay, and it is a symmetric matrix, you all know about it. Now, to understand how the nodes can be eliminated, what we will do is that we will partition this equation, that is the current vector I can be partitioned into two sub vectors. Similarly, the voltage vector will be appropriately partitioned, and then Y bus matrix is also partitioned. After partitioning these matrices, we can write down IA, Ix, this is the I vector, and Ia is a vector, Ix is also a vector. It can be partitioned as the submatrix, Y matrix is partitioned as KL, L transpose M, VA, Vx. That is, when we are doing the partitioning, right, of the system, then when I partition this current vector, then the Y bus matrix is also appropriately partitioned and bus voltage vector is also appropriately partitioned. After this partitioning, we can write down the equations, the two basic equations in the form Ia equal to K times Va plus L times Vx, and Ix can be written as L transpose Va plus M times Vx. That is, this is simply obtained by multiplying these two matrices on the right hand side of this equation. Okay. Therefore, I get Ia is equal to K times Va plus L times Vx. Ix is equal to L transpose Va plus M times Vx. Now, in case this Ix is a null vector, in the sense that all elements are 0. Okay. In that case, what we can do is that we can write down Vx in terms of Va and other elements of this equation. What we do is that you subtract both the sides of the equation by L transpose Va, Ix is anyway 0, and multiply by M inverse. Now, when you do these two operations, that is, you are subtracting both sides by this L transpose Va, right, and then you multiply by M inverse, you will get an equation in the form minus M inverse L transpose V A. It is wrong, it is L transpose V A. Okay. This is equal to V x. Now, we have obtained the expression or equation for V x in terms of other known quantities. Okay. So, that what we do is that we substitute the expression for V x in equation 7.3, right. So, that this V x is eliminated, and the moment we eliminate this V x, you can write down the equation in the form I A is equal to K times V A minus L M inverse L times V A. Okay. And therefore, this equation can be put in the form I A equal to K minus L M inverse L transpose into V A, right. That is, if I write the equation in this form, I A equal to K minus L M inverse L transpose, this is L transpose into V A. Here I and V A have the same dimensions, and this is a matrix, it is going to be square matrix, have the same dimensions as that of the K, and therefore, now I can say that my model becomes I A equal to Y bus reduced into V A. Therefore, this reduced Y bus, you can say this is Y bus reduced. Okay. And this reduced Y bus can be written in the form as K minus L M inverse L transpose. Therefore, here the network which initially had certain number of nodes, and those nodes where there was no current injection, okay, these nodes have been eliminated, and therefore, this is now a reduced order model, and there are no nodes where there is no injection. Actually, I will just illustrate this with the help of a example. Now, let us consider that we have a simple system, is a third order system, let us say, okay, and the Y bus matrix of the original system is minus 3.33, 0, 3.33, 0, minus 7.5, 2.5, 3.333, I can put 3 here also, 2.5 and minus 10.833. This is, let us say, is the Y bus of a system which has 3 nodes. Okay. Now, let us assume that the node number 3 is 1 where there is no current injection, and I want to eliminate that node. What we do is that we partition this matrix, because there are 3 nodes, 1 and 2 and 3. Okay. Therefore, we partition it in this fashion. So, that K becomes now matrix minus 3.33, 0, 0, minus 7.5. Okay. L is a vector in this particular case, 3.333, 2.5, J will be there in all the cases. Okay. And M is minus J times 10.833. Okay. Now, you substitute the value of K, L and M in the expression K minus L M inverse L transpose. Now, we make the substitution here. This is a column matrix, this is simply a scalar quantity, this is a row, but when you multiply this 2, it will be a 2 by 2 matrix, and then subtract this from the elements of K matrix, and the resultant matrix, which comes out to be J times 2.308, 0.769, 0.769 minus 6.923. Now, I have illustrated through a very small example, but this is applicable to any system which may have any number of nodes to be eliminated, and this simplifies the process to a great extent. Okay. Now, our next step will be in solving the multi-machine problem. We have to develop the classical model. When I say it is a we are using the classical approach, we will have to develop the model. Now, in the classical approach for tangent stability analysis, we make all those assumptions which are made earlier. These 5 assumptions which we made earlier, I will just reiterate them. First was that mechanical input power remains constant. Second was all asynchronous powers or damping torques were assumed to be 0. Third assumption was a synchronous generator can be represented by a constant voltage behind direct axis tangent reactance. Fourth was that synchronous power can be computed from the steady state solution of network. And the fifth was the phase angle of the voltage behind tangent reactance coincides with the rotor position with respect to the synchronously rotating reference frame. These were the 5 assumptions which we had made. The next assumption which we will make here is all loads, because in any power system you will have loads at various buses, all loads may be considered as shunt impedances to ground with values determined by conditions prevailing immediately prior to the tangent conditions. That is, in the system we have loads connected, and we will convert the loads by equivalent shunt impedances. Okay, and while calculating these shunt impedances, we will consider the condition prevailing prior to the tangent. Okay, whatsoever was the condition before the occurrence of tangent or steady state condition. Okay, using that condition we will find out the equivalent load admittances or load impedances. Okay, this is very important next assumption which is made. Now, for analyzing the tangent stability or for any stability problem, we always require the initial operating condition or the steady state operating condition prior to the occurrence of disturbance. Now, for a multi-machine system, the steady state pre-fault conditions for the system are computed using load flow. That is a mistake, by mistake it is written twice. The steady state pre-fault conditions for the system are computed using a load flow. Therefore, a load flow for the system becomes a precondition for starting the solution of any stability problem in a multi-machine system. Okay. Now, the model for the system. Okay. Now, the model of the system actually with all the assumptions which we have made, it looks like this. The transmission network is shown here. To this transmission network, we have generators connected at certain nodes. We can show that these are the points at which the generators are connected. There are certain points in the network where the loads are connected. Okay. Now, these loads are represented by constant impedances connected to the reference bus. Now, these generators are replaced by voltage behind transient reactance, direct axis transient reactance. Now, here we will not neglect the armature resistance of the synchronous machine. Okay. Once we account for the armature resistance, then we are representing the generator by a impedance R1 plus J time XD1 prime, R2 plus J time XD2 prime, and we find out the voltage behind this impedance. If you neglect this resistance, then it becomes simply the voltage behind direct axis tangent reactance. But here, when we do the tangent stability analysis, there is no need to ignore the resistance and we can account for it. Once you account for this, then these are the voltages behind the tangent reactances. Therefore, now if you see here, the network which is enclosed in this rectangle is a passive network. It does not have any source now. Okay. All these sources have been taken out. That is, at these nodes we have connected the voltage sources and all the loads have been replaced by constant impedances. And therefore, what we exactly do when solving this problem is that initially you will perform a load flow analysis. Okay. And once you perform the load flow analysis, you will find out the voltages at all these nodes and all the nodes where the loads are connected. Okay. Then using this information, the loads will be converted into equivalent impedances and we will replace the generators by equivalent voltage in series with impedance. Okay. And then this becomes my model which is going to be used for tangent stability analysis. Now, in this case what we have done is that I have shown n generators, okay, and there may be R nodes where the loads are connected. Okay. Therefore, the system may have originally n plus R nodes. Now, when you perform this load flow analysis, you find out the Y bus matrix considering only the line parameters. Okay. Therefore, now when you perform the tangent stability analysis, the Y bus matrix will be modified and it will be obtained considering the machine impedances and these load impedances. Okay. Once you obtain this Y bus matrix accounting for this machine impedances and the load impedances, the load buses can be eliminated. Okay. And therefore, you will be left with only these n buses where the generators are connected. Okay. All the load buses you eliminated and the buses where these generators are connected, they are also eliminated because there is no injection here also. But ultimately, you will need or you will get a model which will have the n nodes where the generators are connected and these are the constant voltages, that is the voltages of constant magnitude. Their phase angles will vary during the dynamic conditions. Okay. Now, for this network we can write down the equations in the form I equal to Y bus E, where I is the current vector or current injected at all the n buses and Y bus is the admittance matrix obtained after eliminating all the nodes. Okay. Therefore, using this we will be in a position to obtain the equations for electrical power output from all the machines, because we know actually that when we have to obtain or we have to analyze the tangent stability analysis, we need the expressions for electrical power output from the generators. Okay. Therefore, using this model, which is having only the n nodes where the generators or internal voltage of the generators are connected, and this exercise is an important exercise for which I have already explained the methodology. Now, here we will represent the diagonal elements of the Y bus matrix, which are called YII, will be equal to magnitude YII angle theta II, which will have the real and imaginary parts GII plus J times BI. Similarly, the diagonal elements will be shown as Yij, magnitude Yij angle theta Ij, Gij plus J times Bij, and these voltages EI will be written as EI angle delta I. Now, here I am not writing this prime, right, because once we understand that this is the voltage behind the direct axis tangent reactance and the stator resistance included, okay, then because writing every time E prime is little what inconvenient. Okay. Therefore, we consider that these are the internal voltages and the magnitudes of these voltages will remain constant. Now, we can find out the electrical power output PEI by this basic equation, that is the real part of EI II star, real part of EI II star. This is very important. Now, here you look like this, that this is the bus at which the voltage source is connected, say EI, this is ith bus. This II is the current which is injected by this voltage source. Okay. And we know actually the complex power injected is equal to Pi Si equal to Pi plus J times Qi, and this can be obtained by the formula always, and then in this particular system EI into II conjugate. Star stands for conjugate. Okay. And therefore, when I take the real part of this EI II star, that becomes the electrical power output from the ith generator. Now, we substitute the expression for II. The expression for II is we have the vector II can be obtained as yi1, yi2, yin multiplied by this vector E1 up to, that is, you have this is the ith row of the Y bus matrix, and when you multiply this with the voltage vector, bus voltage vector, you will get actually this II as yi1 plus yi2 E2 plus yin En. That is, we can write down this II as summation of Yij Ej, where j varies from 1 to n. This is the way we will be writing the expression for II. Now, when you make this substitution here for the expressions for II, that you have to take the conjugate of this current and then perform simplifications, you will get the expression for PEI, that is electrical power output of ith machine, as EI square GII plus j equal to 1 to n ei ej cosine of theta ig minus delta I plus delta j, and j will not take the value equal to I, and this equation is valid for I varying from 1 to n for all the machines. That is, you put I equal to 1, 2, 3, 4, you will find that you will be in a position to get the expression for electrical power. This is a very important expression, and for n machine system we will get n such equations. Now, if you just look at this expression carefully, you will find actually that this depends upon the magnitudes of all the voltages which are known to us. They remain constant during the tangent stability analysis, that is during the tangent period. These are the GII. There is one term which is missing here actually, just please correct it. It is YIJ. There will be EI, EJ, YIJ will also be there. Okay. Cosine of theta ij minus delta I plus delta. Therefore, this YIJ is also known to us. Only thing which is not known will be the quantities which vary, the delta I, delta ij. Therefore, what happens is that these angles will be computed by using the numerical technique, and at the end of each step of computation these angles will be known. Therefore, we substitute the value of these angles which are computed when you solve the swing equations, right, and you get the expression for PEI at each step. Now, once we know the expressions for electrical power output of the machines or all the n machines, then we can write down the n swing equations. Okay. The swing equations for each machine will be 2 times Hi upon omega s d omega I by dt equal to PMI, that is the mechanical input to ith machine, minus the electrical output of the ith machine. Again here Yij term is missing. Okay. That is what we have done is that this expression is same as I have compared. This is the expression for electrical power output from ith machine. Okay. Then this is the main equation, and we write down this d delta I by dt equal to omega I, which is equal to the actual speed of the rotor minus synchronous speed, because d delta I by dt is the excess speed of the rotor, right, and this is excess over synchronous speed. Therefore, I am writing d delta I by dt equal to omega I, which is equal to d theta I by dt minus omega I. Okay. Therefore, what we see here is that we have written two equations, two first order equations for one machine, and therefore, if you have n machines in the system, then you will get total 2n such first order equations. Now, we need the information of what is the mechanical power input to the machines, PMI, and we assume that this PMI is constant over the tangent period. That is, mechanical power input to all the machines are assumed to be constant, right. Therefore, there is a necessity to find out what will be the mechanical power input initially. Okay. Now, how to do it? Well, under steady state conditions, the electrical power output is equal to the mechanical power input, and the system is in steady state condition, that is the derivative terms on the left hand side of the equations are all 0. Okay. Therefore, with this condition we can write down the expression for mechanical power input as PMIO equal to EI square GIIO. I am putting O here, means this is the element of the Y bus matrix before the occurrence of transient. Again here you have Yij, okay. That is the complete expression. Wherever actually angles were delta I put delta IO, delta JO. Now theta IJO. Here you will find actually that when the system is subjected to disturbance, okay, therefore during fault conditions the Y bus matrix of the system will be different. During post fault condition it is again going to be different, right, and therefore we will have three different Y bus matrices, one pre fault condition, one during fault condition, third post fault condition. Now here to compute the mechanical power input, initial mechanical power input PMIO, right, we use the conditions which are prevailing in the system before the occurrence of disturbance, and this is I am denoting by putting a further subscript O, okay. Now the equations which we have written were 2n equations. These 2n equations can be written in the general form as x dot equal to a function, a non-linear function x comma xo t, where x is a vector of dimension 2n into 1. X is a vector of dimension 2n into 1, where n is number of machines, and these are all first order non-linear differential equations, or we can say a set of 2n first order coupled non-linear differential equations. They are all coupled. Now x transpose is actually the x is the state vector. The state variables are omega 1 delta 1, omega 2 delta 2, omega n, right, and let me just summarize here how we obtain the mathematical model of the system. The first step is that for the given system you perform a load flow study and find out the initial steady state operating condition, okay. Once you have done this, the next step will be to replace all the loads by constant impedances. Then next step will be to, knowing the information which you obtain in the steady state condition, you replace all the generators by constant voltage behind a impedance R plus J times XD prime, okay. Once you have done this thing, you can eliminate all those nodes where there are no current injections or no sources connected, okay, using the matrix algebra. Once you have done this thing, you can find out the set of non-linear coupled differential equations for the machine, okay. Once these equations are there, our task is to solve these equations using numerical technique and plot the graph relating deltas versus time. That is, we have to plot swing curves for all the machines, and then we examine these swing curves to see whether the system is stable or, okay. This is what is step. Now here, before we do all the tangent stability analysis, one has to perform some preliminary computations. The preliminary computations to be done are: all system data are converted to a common base. This is a pretty important requirement, that when you assemble the system data, you will find actually that data are given on the basis of their nameplate ratings. Suppose you have a generator of 500 MVA, okay, then the generator parameters will be given on the basis of nameplate rating of the machine, okay. But once you are solving a system, you have to convert all the data on a common base, and the common base generally chosen is 100 MVA. Okay, 100 MVA is common because it looks to be little convenient for computations. Okay, otherwise there is no such hard and fast rule. You can choose the common base, and when you say the one is MVA base, another is the voltage. Voltage in a particular circuit you will choose, and then you will compute the per unit values of all the system parameters on common base. The second step is the loads are converted into equivalent impedances or admittances. The needed data for this is obtained from the load flow study. Okay, this is what I already told you. Now, how do we convert actually the loads into constant admittances? These steps are also important. This we can write down here, that at suppose the load is represented as PL plus J times QL. At any bus as load is PL plus J times QL. This load can be written as VL into IL star, because this is the complex load, right, and with this can be written as the bus voltage of the load bus, the voltage of the load bus into the conjugate of the current drawn by the load, IL star. Okay. Using this expression, we will compute the value of elements of the admittance which is going to replace the load by a constant admittance. Now, the admittance will be written as YL plus J times YL equal to GL plus J times BL. Okay. This can be simply obtained that in this expression you can substitute the value of IL. We know that the current drawn by an admittance is equal to admittance into the voltage. And admittance, load admittance multiplied by the voltage, that will be the current. And admittance is given by this formula. Load voltage is VL. Therefore, IL star is going to be VL star into YL star. IL star is VL star into, therefore, VL into VL star becomes VL square, and IL then YL becomes GL minus J times BL, YL star. So, that we can write down this load as VL square into GL minus J times BL, right. And therefore, using this expression, equation 7.8, right, we can say that the load admittance is equal to PL minus VL square minus J times QL by VL square. That is, you can say that the real part is PL divided by VL square and reactive part is BL divided by QL minus VL square. Okay, the proper sign is to be considered. Therefore, this is one important step, and these voltages VL which are substituting in this expression are the obtained by load flow analysis. Okay. Another computation which is required to perform is the voltage behind the tangent reactance. Okay. Now, here you can use this expression EI prime equal to VTI plus J times XDI prime into II. Now, here I have not considered the armature resistance, right, but you can modify this by putting here instead of J times XDI prime, we can put here Ri plus J times XDI prime. Okay. And since these all informations are known, current is known, terminal voltage is known, you can find out while finding out this internal voltage, we will use this expression. The current injected by the generator is Pi minus J times Qi divided by Vti star. This is a very standard equation which can be used to compute the value of current, and this current is required in the equation 7.10 to compute the internal voltage. The internal voltage which you compute, right, will have its magnitude and phase angle, right, and this phase angle which you get become the initial value of deltas. Okay. And the magnitudes will remain constant during the tangent. Now, once you have done these preliminary calculations, okay, we obtain using this information the swing equations. Now, you know that we require swing equations under 3 different conditions. One is the pre-fault operating condition, second is the during fault, and third is the post-fault. And therefore, when you solve these swing equations, suppose I start solving the equations at time t equal to 0. Okay. Now, if the perturbation or disturbances occurred at time t equal to 0, right, then immediately from that initial steady state condition, I will be using the swing equations, I will be solving the swing equations which are applicable during the fault on period. Then once I know that, okay, after this much time the fault is cleared, right, it means the moment I reach that particular point, I will change over from the fault on period swing equations to post fault swing equations and continue to solve it, right. Now, one should know actually that suppose the fault occur in the system, how to obtain the swing equations which will be applicable during fault conditions. Pre-fault conditions we have already obtained. Now, the faults can be symmetrical faults or unsymmetrical faults. Now, in case it is a symmetrical fault, then the problem is bit simple. If it is unsymmetrical, then also it is not difficult, because we have already seen how to account for the unsymmetrical fault. Now, if it is, suppose I take fault at a particular bus, let us say that fault occurs at a particular bus, then voltage of that bus will collapse, it will become 0. Therefore, the occurrence of fault at a particular bus is accounted by considering or by setting that voltage of that bus to 0. Okay. Then once the voltage of that bus becomes 0, we have to modify the Y bus matrix which will be applicable to this period, this particular fault on condition. This modification are not difficult. One can, once you see that a particular bus is grounded, okay, looking into that condition you can modify the Y bus matrix. Now, simplest way is that if you have a Y bus matrix or the pre-fault condition, then if suppose at a particular bus, let us say bus number 5, if suppose there is a 3-phase short circuit, then the row and column corresponding to the bus number 5 can be deleted from the pre-fault Y bus matrix, and the remaining Y bus matrix, right, will become the Y bus matrix applicable to post fault condition. In fact, actually suppose one particular bus is grounded, or since it is shorted it gets grounded, the number of buses which remain now will become less by 1, right. Therefore, Y bus matrix also reduce in dimension. Similarly, once you consider the post fault condition, right, you can obtain the Y bus matrix during the post fault condition, because under post fault condition what happens, one line may be out. Therefore, for the remaining system you have to find out the Y bus matrix. Now, this Y bus matrix need not be assembled fresh. One can modify the existing Y bus matrix by modifying the elements of Y bus matrix. Some elements will be affected. For example, actually if suppose there is a Y bus matrix, and if the line connecting the node 1 and 2, right, is stripped, okay, then what is that is going to affect the, or which elements of the Y bus matrix will be affected? That is, Y11 will be affected because that line is out, Y22 will be affected, and Y12 will be affected, others will not be affected, right. Therefore, once we know that particular type of line element has been removed, right, you can easily find out the Y-bus matrix applicable during the post-fault period. And once we know the Y-bus matrix which are applicable during post-fault, during fault and during pre-fault conditions that you already know, because our equations, that is the equations for electrical power output, are written using the reduced Y-bus matrix. Therefore, this reduction process has to be done for all the three conditions: pre-fault, fault on condition and post-fault condition. Now, I will suggest you to refer to these problems or these two examples which are given in here. One example is given in the book written by P.M. Anderson and Foude, Power System Control and Stability Volume 1, example 2.6 and 2.7, these two examples. This is example which is very commonly used for illustrating the tangent stability analysis. It is a 9-bus system. It has total 3 generators, 9 buses. Okay. And in these two examples, all the step-by-step computations have been carried out to illustrate the steps involved in solving the tangent stability problem. One more simple example which is given in the basic book on power system analysis, there is Elements of Power System Analysis by Stevenson. Everybody is aware of this book, Stevenson. Here he has solved a 5-bus system. Okay? And in this 5-bus system, he has illustrated all the steps which are required to obtain the complete tangent stability solution. Now, once the model is obtained and you solve the swing equations, set of coupled swing equations, you will get the swing curves. Okay. The swing curves will plot actually as delta 1, delta 2, delta 3 as function of time. Now, to examine whether the system remains stable or not, we have to see the relative variation of the swing curves. That is not the absolute values of delta 1, delta 2, delta n, that is important. What is the relative value that is more important? Suppose the two machines may accelerate simultaneously, okay, but the angles may remain very close to each other, or angle difference may remain very close, then system is not losing synchronism. Therefore, when you examine the stability of the multi-machine system, we have to examine the plots of relative angles. That is, we plot actually delta 1 2, that is delta 1 minus delta 2. We plot delta 1 minus delta 3, suppose it is a 3-machine system, there are only 3 angles involved. And once these curves are plotted, in case actually the curves, or you can say delta 1 2 reaches a maximum value and decreases, it shows the stability condition. In case delta 1 2 increases continuously, it shows unstable condition. Okay. With this, let me conclude what we have done today. We have given, or we have studied the basic steps involved in analyzing the tangent stability of a multi-machine system. Here we have used a classical model for analyzing the stability. I have mentioned that how do we obtain the required models for pre-fault, fault on and post-fault operating conditions. Okay. And the swing equations which we obtained for the system are solved by using numerical techniques, and The stability of the system is understood by examining the swing curves which we plot, and particularly the swing curves are relating the relative angles of the machines. Okay. Thank you very much.